that this problem exists. Um, the and one of the reasons is for this is I mean, maybe one of the most famous and known reason is like two things can be at the same place at the same time, kind of thinking. And I'm referring to what is called the two slits experiment. I'm not going to go into exactly what it is, but you have an experiment like this, where you have a you set up an obstacle like this, and then you make two thin slits here, and then you send a beam over here. Let's say if you would send a light beam towards a slits like this, and then you have a screen in the background which catches this light beam. Light is a wave, so what they will do is like the beam will go through this slits here, and it will go through that slits here, and when it passes the slits, it will at the surface, the light will bend out like this, and this slits here will cause the same thing. And this is because, like, if you think about light, it's a wave, and that wave is what we call the field. A field so it's a wave like this in 2-dimensional or 3 dimensions. And a field is something that is defined everywhere in space. What do I mean with being defined everywhere in space? Well, think about a room. You could put a thermometer into this room, like this, and measure the temperature. And you could do this very precise. You could go to the corners here, and you could go along the sides here and measure them. And if you have a large enough room, you may find that in different spots there is a different temperature. So you can have a temperature gradient in the room here, and most of the time, all of us have a temperature gradient in the room, where at the ceiling the air is a little bit hotter, and in the bottom it's a little bit colder. But there is no point in space where there is no temperature. There is a temperature. You can read off a temperature at every single spot in the room, and that means temperature is defined everywhere in the room. And that is what we mean with a field. This is a temperature field. And when you say it's a temperature field, you mean temperature is defined everywhere in the room. And the same thing is with a light wave. Is defined everywhere. A light wave is defined everywhere in space. So when the light wave comes to the slits, it's going to pass both slits. And of course it's not going to pass where the block is. I have to check the time here. Okay, I have to hurry. The split, where it passes the split, because it's a wave, it will spread out from this thing here, and then on the screen, because the nature of waves is such that they can overlap each other, and if you have a wave that goes up like this, and then you have a wave that goes down like this, this is one wave, and this other wave. So this is wave A, and this is wave B. So if you have wave A here, and the wave is going up, and then you have wave B here, and the wave is going down, then they're going to cancel each other, and the result is going to be flat. Or you can have the waves, wave A and wave B being synchron. Then they're going to enhance each other like this. And depending on where on the screen you are, you will have different regions where the waves are in phase or out of phase with each other. And that means that since it's light, and if it's flat, 0, then there is no light. So there will be dark areas and there will be light areas on the screen. So it will look something like this. And that's called an interference pattern on the screen. There will be beams like this. And the key thing is, this is a wave behavior. Okay? Now, if you take a fundamental particle, a quantum particle, and send them one by one to this screen, what will happen is you won't see this thing, a wave. You will see something registered a position. Like I said, you can only register positions. You can't observe waves. You only observe positions. And if you do this many times together, the positions you observe will correspond to a wave interference pattern. And this means, what this means is that we're asking what the hell is going on here. And we don't really know, but what we do know is that this is corresponding to things which is already well known to us, and that's called wave mechanics. So while I was recording, I ran out of memory in the phone, so the recording stopped. So I'm going to, and of course then I did all the writings, so I'm going to have to repeat what I was saying. The last thing I said was that these interference patterns corresponds to, no, not into, yeah, this is, I'm going to step ahead. These patterns on the screen produced by these detections of positions is corresponding to an interference pattern of a wave. That's what I say. And waves are well known, or at that time when quantum mechanics was still being formulated, wave mechanics was very well known to physicists. So they immediately recognized this as like a wave phenomena. The thing here, the why we're talking about waves in quantum mechanics is not because we have observed any wave directly. We have interfered waves. And I'm not going to say we have interfered the existence of waves for a very specific reason, which I'm going to come to very soon. But wave mechanics, the behavior of waves can be used to partly explain this experiment. It can be used to explain why you see a pattern that is strikingly similar to a wave interference pattern. The problem with this is that if you're using wave mechanics to describe this experiment, then we have a problem between the observed events here, that we we observe the thing at the position, and that position we observe it is from a source where we send out what we believe to be a particle. That's the first observation. The second observation is when it hits the screen. That's the second observation. So we have a situation like this, a source and a pattern. And as I said before, we don't know what happens in between here. If we want to know that, we have to look. We have to look at the time period there. But we didn't. So if the reason is a particle, then we could use this reasoning here. But you have to understand that this reasoning is not part of early 20th century reasoning anymore. This is pre-20th century reasoning. And what these concepts, the reason why you can safely assume that the ball was there is because persistence of existence. This is an assumption. We assume that there is persistence of existence, and when we presume that existence, then we make an inference that it must have been in between there. And like I said before, it's a perfectly reasonable assumption to make. And it's never been questioned before until early 20th century because of experiments like this. And the reason this assumption is questioned is because if you believe this is a particle, because it was observed here at that position, and then you observe it at a position here, you may say like, okay, it has a fixed position, so it must be a particle. I observed it at a fixed position here from the source. And at the target. I observed something at that very specific position, which you call the particle. That reasoning breaks down when you come to the slits, because if it's a particle, then if it's a singular particle, then if it is an atom, as the Greek said, then it has to pass both slits. Because the description between two observations, the description we're using here, this is an observation and this is an observation on the screen over here. The description we're using in between those two observations is a wave. We describe it as being a wave in between here. But there is no observation made there. We observe a particle sent and we observe a particle at the source, and we observe a particle at the target. And in between we describe it as a wave, but we haven't seen any wave. The only reason it's described as a wave is because it looks like a wave in the pattern that emerge after sending many particles. So it's a convenient way to describe the experiment as a wave. There is another way, way to describe this, and it's called it's by using matrices.